And just to kind of summarize, like I do like visible, and then on either side looking for 3, so longer than visible, of course, is IR. You already have this. But micro, and then radio, and then the 3 on the shorter side is UV, and this is so exciting. We're going to talk about different forms of UV, A, B, and C, and then we have X-rays, and then we have gamma. And there's called an inverse relationship. So that's to say, so for instance, gamma, which one has the longest wavelength?
Wait, I'm on the wrong page.
Yeah, I think we actually answered this one, so.
Oh. Okay.
So which one of these 7 has the longest wavelengths?
The longest is radio.
Yeah. So long wavelength and short wavelength. And with regard to frequency?
The frequency is the highest for gamma.
Yep. So high frequency, yep, and then low frequency here. Yeah. So for what it's worth, so there's a few questions on the next slide about this figure. This actually is what we call a radiation curve. This is a radiation curve where along the x-axis, got my x and y mixed up, along the x-axis we have different wavelengths. So which one's high energy? Over here or over here? So these are wavelengths.
High energy.
High energy is the shorter wavelength.
So the left side, or
Yes.
yeah,
The left side. Yep. This is shorter wavelength and high energy. Yep. And actually, it's kind of exciting. In the next slide, we're actually going to kind of associate some energies with these different wavelengths according to an equation. And then over here, we have low energy and long wavelength. Yep. So this is kind of neat. This actually is our visible right here. So what is, up here it says, we have these 2 sectors. Let's put it this way. What is just a little bit shorter wavelength than visible?
Ultraviolet.
Yes, yes. So I'm going to put UV right there, exactly. And actually, the UV, the amount of ultraviolet radiation coming from the sun is underneath this curve. Okay, because this is, I should have explained along the y-axis we have intensity. So the intensity, for instance, of, I don't know, just pick one of these ultraviolet wavelengths. The intensity of this ultraviolet wavelength would be right here. The intensity of this one is right here. Okay, the intensity of yellow is right here. Okay, so that's how that goes. So that's ultraviolet, and then what's a little bit longer than visible?
Infrared?
Yep, and this is IR. So on the next slide, we'll go ahead and answer the your turn question. So which of these, just guess maybe, or you can actually see over here, which of these 3 sectors, UV, this is this area, visible, this is this area, or IR, this is this area, which one is the most, the greatest amount?
Is the most what?
Is in the greatest amount, the greatest area.
Oh, it's infrared.
Mm-hmm, yep. This actually, this pie chart over here is reflecting this, no pun intended. So it's actually showing that the amount of energy, the volume of energy coming in that region of energies.
So those are the only 3 types that are coming from the sun.
Those are the 3 main parts. And the thing about the sun actually, as I understand it, is actually there could be even shorter wavelengths, but there's not much area under here. And the sun actually also sends us some I don't know if I've heard much about the sun's microwaves, but I've definitely heard about the sun's radio waves. So the sun is kind of sending us in this area, but it decays. It's not as much as, and all stars are like that. So I kind of feel like we answered this. Which type of electromagnetic radiation comprises the greatest portion of energy of the sun?
IR.
And which was the most intense, though? Intense would be
visible.
Exactly. Yeah. Intensity would be along the y-axis. You got it. So we talk about the dual nature of electromagnetic radiation. Now this says, sometimes we says light, but light to me is are those 7 forms of electromagnetic radiation. They have both a wave-like and a particulate-like property. So with regard to their waves, we can kind of think of like dropping a pebble in water and the water being disturbed as you crest the trough, crest the trough. You can get a wavelength, you can even get a frequency. Okay, so that's kind of the wave-like. In fact, I brought this along to kind of show us the wave-like property of light. So light is directional. It's what we call a transverse wave. That's to say it moves up and down. Like literally, when we talk about photons, that's the particular part. These photons literally move up and down, and they move forward. This is so awesome. Okay? So when you buy sunglasses, a lot of times you'll get the polarized sunglasses anymore. And the polarized sunglasses actually have built-in it's like a picket fence. So basically that way that picket fence is to go ahead and just only get that light that's going up and down. It's like a picket fence with narrow. So if I have light coming along like this, guess what? It's not going to get through our sunglasses. Okay, and that is great with regard to glare. So I brought these to kind of show you. Now, not that you should be destructive and break your sunglasses or anything like that, okay? But these would be two picket fences, actually. If I go like this, the picket fences are going the same direction. I know it looks a little darker, okay? So you can either look here or look there. But now, if I take one of my picket fences, they're both in the same direction, and if I start to go ahead and rotate it, okay, with regard to light getting through, okay, it's going to be less and less. So here I go, here's my rotation. And you can do this with your sunglasses too. So when I go ahead and get to basically a right angle of my 2 picket fences, nothing's getting through there. That's how polarized sunglasses work, the polarized lenses. And then if I bring it back around, I line up my picket fences. And
how are you knowing on those that they're? Can you see the lines? Or something?
No, I can't see them. I just before we started, kind of just held
line them up.
Yeah, kind of line them up. And if your sunglasses accidentally break, you can actually do that with your sunglasses too. But if you make both picket fences go opposite directions, you know.
So these were broken in half, and you did that. Is that only with nice sunglasses? Or
what's that?
Is that only with nice sunglasses?
I think most sunglasses are polarized anymore. And if you have 2 pairs of sunglasses, I think you can do it too. And if you've ever been trying to read an electronic display and your sunglasses, it's just oh my gosh, fine. So you take off your sunglasses and you can get the display. What's happening basically is the device, the light from the device is directional, and it's not matching with your sunglasses. So all sorts of practical little things there. So the packets of energy we call photons. Just a minute ago I said that packets of energy are literally moving through space up and down, okay, and we call those photons. Now the thing about a photon is it's kind of, a minute ago you told me that with regard to energy, ultraviolet has more energy than infrared, ultraviolet has more energy than infrared has less energy. And kind of think of the energy that those waves have are associated with kind of the energy that packet has, the energy that photon has. So all photons aren't created equally. You look at a UV photon, it's no different than eye level. And so kind of along those lines, we talk about how the energy of a photon is step-like. It's step-like. So the opposite of being step-like is being continuous. So this is to say this cute little cat.
Oh, I love that example.
This cute little cat can be here or here or here or here, but the cat can't hover between those. And that's kind of how the energy with electrons is.
And that's kind of like what the sunglasses are too. Like they can pass through a couple of zero commas.
I don't think so. I think this is like the photon part, the packet part, and the polarized lenses is kind of like making use of the wavelength.
Okay.
Yeah. So the shorter the wavelength and or the higher the frequency, the more energetic the radiation. Actually, that's consistent with what we've been talking about. So if we pick on ultraviolet being more energy than infrared, you would tell me ultraviolet has a higher frequency, a shorter wavelength. Okay, things to the, and I always draw them in that order for some reason. I put the most energetic, the shortest wavelength, the highest frequency over here. All right. So we have this, especially with stars. Have you ever seen a red star and then a blue star, sometimes a yellow star?
I didn't know there were different colors.
Yeah, they do have different colors. And their colors actually are of the stars an indication of the temperature. Now this is where you kind of have to take out your, we learned it's red hot or cool blue, but it's just the opposite. Actually, if something is a red color, it's actually the coolest. And if you think of our Roy G. Biv, red was the longest wavelength and it's the coolest, it's indicating the coolest temperature. It's the same thing.
Because, okay.
Yep.
Must be cool.
Yep.
That looks like, is that a torch?
I think it's, these are just Bunsen burners that have different different fuels or different fuel to oxygen ratios. But it does look like a torch. Wait till we use that. Have you ever used a Bunsen burner before?
Yes. Okay. And my boyfriend had an acetylene torch, and he had to play a little bit, and he had to get it for
the different colors was because like,
yeah, you have to turn it down to like number 4. Yeah.
Did it start as the?
Yeah, it started kind of
that's
like
neat.
When you lit it, you want.
Yeah. I don't like flame, so like. So energy is proportional. Now, once we say something's proportional, that means as one goes up, the other goes up. So energy is proportional to frequency. So frequency increases, energy increases. Anytime you see inversely proportional, that means that as one goes up, the other goes down.
So the longer the wavelength, the less energy.
Yep, the longer the wavelength, so I put my finger up, then the less the energy. I put my finger down. Yep, you got it. So there is this little formula. So E, of course, is energy. That little nu is frequency, and the H is what we call Planck's constant. And it's at the bottom there. So we would use this if you know the frequency. So we're all about kind of plugging into equations. So we know H because it's going to be down here, that's Planck's constant. And if we know the frequency, then we'll do it this way. Now, if we know the wavelength, we can rearrange this, okay? And we aren't rearranging it. Actually, all we're doing is we're counting on the fact that the frequency is equal to the speed of light divided by the wavelength.
So it's just exactly the same thing.
Yes, it's exactly the same thing. So if you know the frequency, we use this one. If we know the wavelength, we use this one. So it depends on what we know.
Where did this Planck's constant come from?
That's a good question. There are all sorts of constants in physical science.
Somebody made up.
Not made up, sort of, but by experimentation. So they just basically ran a lot of experiments and found this trend. A lot of times experiments can be run and then you can plot your results, and then from whatever your plot comes out, a lot of times it's the slope of the line that relates the two quantities. So it's not just made up, but I like to tease that that is Planck's constant in this universe. So if you're a multi-universe believer, which I think I am, if you're in a different universe, the rules are different for everything. So it could actually be a different constant. But that's our constant.
And C was speed of light.
C is the speed of light. And that was the, what did we say, 30 million, I want to say, meters per second. That's the speed of light. All right. So, using that information, let's see what we can come up with here. From the previous slide and those equations we saw, calculate the amount of energy, E, that's present in a wave of red light and blue light. So, brought mine in today. So we're going to use that second one. Does that sound right? Where energy is equal to, what we had? Planck's constant, the speed of light, divided by the wavelength. And this is one where, if you brought your calculator, we'll definitely get some use with scientific notation here.
So for red, you're using 700, and for
Yep.
blue, you're using.
I think I'd go 400, even though I think that's violet, but we'll go with the extremes. So, but 700 nanometers, how many meters is that?
Nano is 1 billion.
So 1 meter over 1 million nanometers.
Wait.
What's that?
Where'd you get that number from? Or 1 meter over, is that?
1 million. Yeah, you told me 1 million, right? Yeah.
Is never 1 million or 1 million?
It's 1 million. What? Did you say 1 billion?
Yeah.
No, it's 1 million.
1 million.
I got 7 times 10 to the minus 4th meters. And I'm going to use the same pattern if that's okay. So how many over here? What would 400 nanometers be equal to in meters?
Okay, sorry. So 400. About 400 divided by 1 million.
Yep.
4 times 10 to the negative 4.
So let's do the violet first, and let's plug in. So E is equal to, I'm going to go on the previous slide and grab that Planck's constant, 6.626. So my H value, my value for H is going to be 6.626 times 10 to the negative 34ths, and that's joules, and then also is joules times seconds. And what do we say the speed of light is?
30 million meters per second?
So I think I'm going to go with 3 times 10 to the,
Oh, 30 times
3 times 10 to the 7th, yeah. That sounds right.
over 7
Meters per second, yep.
7 times 10 to the negative
Let's do violet first. So let's go 4. That's okay. 4 times 10 to the negative 4th. And then units there are meters. And let's cancel the units that can cancel. So what units do you think can cancel?
meters. You have to square seconds?
Nope, because we have per seconds or seconds in the denominator.
Those are in the, okay, so those will cancel.
Yeah, they cancel. And just units of joules, which is awesome. So let's see if we can both get the same answer on our calculators.
Is that what you got?
Yeah. Is that what I got for you?
It's 37. 1.1. Oh, 10 to the 8th. Okay.
Oh, maybe. You're right, it must be because that's not that one. Wait, so wait, at 475,
Oh, 475. Okay, yeah, so we're in purple, they're in blue, so we'll do 475. But where do they get -9?
yeah, because they left it in, they just said the difference between nanometers and meters is, not wrong, you're right, is a billion nanometers.
Okay.
So that's 10 to the 9.
Okay.
So that's right, actually.
Okay, now let's see.
So I'm going to change mine. This guy up here shouldn't be the minus -4th. It should be the -7th. Goodness gracious. I thought my speed of light was wrong. And the speed of light is actually 8th. 7. Still going to be, and they went with, oh, I see, yeah, we did, I wanted to do the shorter wavelength first. So that was their second one. Okay, so what I got for this one, I got 4.97 times 10 to the -19 joules. I'm fine with it.
I'll buy that. So nano is 1 billion.
Yes, yes, you're right. Milli is 1 million. No, micro, I'm sorry. Oh my gosh. Micro is 1 million and milli is 1,000. Okay? Sorry about that. I'd say it won't happen again, but I'd be lying. Okay, so we're going to go to the next part of lecture notes, and we're going to talk more about the ultraviolet. And I told you there's actually 3 parts. I'm learning more, like things I didn't really know, I'm learning in this class. So UVC this is the wavelength. And actually it is the highest energy, so you know it's the shortest wavelength. And then the other word over here is that, but fortunate to us, this energy from the sun is actually absorbed by ozone. So what's the formula for ozone? O3, exactly. So O3, but also just regular old molecular oxygen in the stratosphere. So where is the stratosphere relative to the troposphere?
It's right above.
It is right above. And then UVB is.
But there's like a hole in the ozone layer, right?
There is a periodic hole in the ozone layer. Yeah, and the hole is at the poles. So it's not just everywhere.
So there you can get really bad dirt.
I would think. I think that that's a good point. One of the things actually your book talks about is the UV index, and it doesn't break it down to UVA, UVB, UVC. It's just the UV index. So that would be location, and that would be weather, and the time of year. It's interesting. And the springtime, when a hemisphere, when we're bumping up against springtime here in Alaska, then that's where the ozone hole is.
Good. I was up in the Arctic last summer actually on a trip, and like the sun never set, and like it was like a 9-day trip, and on the 3rd day I left my sunglasses on the beach. And we were in pack rafts, like in boats. And
so you can't go to the store and get...
Yeah, we were out in the middle of nowhere, like a 3-hour bush plane flight. And like the sun was reflecting off the water all day, every day. And I was just like, I would look like E.T. I had my hat and then like my buff like this, but my eyes weren't protected.
Like exposure is length of time and intensity and everything. So it was the summertime though, because the sun didn't set?
Yeah.
Okay, so the ozone hole isn't
as bad in the summer. Is it spring, isn't it?
Yeah, because it's the transition from the clouds that kind of tie up the CFCs, the chlorofluorocarbons. They're called polar stratospheric clouds, and they are in place all winter long. And then the transition between winter and summer, the clouds break up. So kind of all at once we have a dose of CFCs that we're tied up. So CFC and chlorofluorocarbons. So UVB is medium. And UVB, you can read in the textbook. I just think it's so interesting. I've heard Amber talk a little bit about this, but the UVB, it's not as energetic as UVC. Hopefully UVC never gets to us, but UVB actually will only penetrate the first part of our skin. And then UVA is the least energetic, but UVA, as I understand it, is what gets down into our skin, and it actually causes the mutations that end up giving us the sunburn. So UVA definitely gets through the Earth's atmosphere. UVB, as this slide says, is mostly absorbed by ozone, okay, but not all. Okay, so if we were going to arrange UVA, B, and C in order of increasing frequency, what would that look like? Increasing frequency.
So lowest frequency is UVA.
Yes. Yep, I agree. So this is the lowest. Very good. Lowest frequency. This is the highest frequency. How about in order of, is the order of increasing energy the same for frequency? So how about increasing energy?
Increasing energy. The highest energy is UVC. So the lowest UVA, UVB, yeah.
Yep. So I think so too. So because this is the lowest energy and this is the greatest energy. Should you use a sunscreen that claims to protect you only from UVC? No.
It's the one that just gave UVA.
Right.
Oh. Are they both?
Well, UVB, both of them.
And UVA.
But what's up with UVC?
UVC never gets us.
Right. Very good. Ding, 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 ding. All right. So on with the next part. Like I said, this one sounds thick, so let's get done. So let's look at ozone, O3. Okay, and this could be incoming energy from the sun. Sun sending us all sorts of energies, but it's interesting how matter, in this case O3, and energies interact. They're like specific to each other. So like N2, nitrogen, ultraviolet doesn't affect it, but O3, ultraviolet does affect it. So this is kind of neat. You see the, okay. So UVC, you told me, was the most energetic. It's got the shortest wavelength. And actually, as it works out, it can break apart O2. Okay. So the O3 bond that you're seeing here is even not as strong as the O2 bond. So a little less energetic, UVB can break apart ozone. Which, at first blush, you're like, well, ozone, that's bad to break it apart. But actually, it kind of regenerates itself as long as there's no CFCs involved. So what this kind of shows you from left to right, this shows you kind of the agitation of a chemical bond here between two of the oxygen atoms. That agitation then can lead to splitting. So it begins to vibrate the bond.
That's how sunlight can affect ozone.
The ultraviolet in sunlight breaks ozone. Yep. So let's see, blah blah. So UVC, more energetic, shorter wavelength, breaks the O2, the stronger of the two types of bonds. O3 bonds are weaker, and so the lower energy photons, UVB, can break those bonds. So how much more energy does 242 nanometer photon have compared to a 320 nanometer photon? So how are we going to go about calculating energy?
The 320 goes.
Well, I think that, no, because those, how is wavelength related to energy?
Wavelength is inverse.
Does this look familiar? You're right, it is inversely related. It's inversely related like this. So how could we compare the two energies? Now this is going to be constant. Whether, do you know what I'm saying? Like whether you're doing I think we have to take the inverse of the, if you just take 1 over the wavelength of 320 nanometers, compare it to 1 over the wavelength of 242 nanometers. That makes sense? But to finish the whole thing, I think, to me, you kind of go back to this equation and do like what we did with red and violet. What does your turn do in the 3.9? That's a little bit like glass. We won't do it, but let's just look since it's just you and I. What are we doing?
So they started by dividing them?
Well, that's what you said. Just kind of look at and use and subtract and we divide it. So what they did was they realized that what's at the crux of being different between the two wavelengths, or energy, is the wavelength. And so they just took a ratio of these two values to compare them. I don't buy that. Because you told me that it's energy is inverse from the wave to wavelength, so we'll just focus on wavelength. They said 1.3 times is about 130%.
But so here they did, this is age, and that's speed light divided by 2.2.
They converted that into streamers.
Either that, and then this one, the same thing, and then they divided that. This is the turn rate.
They get the same number. And they took 2 different ways. So bottom line was that there's a factor of 130% more energy between the UVC and the UVB.
How do you know to divide 320 by 242 and not the opposite?
Well, if you divide it, if you did the opposite, then you end up with, go ahead and divide by that. So in that case, we would say that the UVB is 75% of, yes, UVC. So there's nothing wrong in doing the other ratio. We just have to say it differently.
Like if that, like these things confuse, like I would never know if that was on a test, that was a, what was that?
I'd be surprised if that was on the test. But
Or like stats, as soon as they put an equation in the words, I'm just like, what?
yeah. I hope like science is different than stats, and that science, you seem like you're good at finding your way through a problem and you think through it. Stats to me, it just seems so unconnected to things sometimes when I took it.
Yeah.
So hang in there. The real life application is better. So picture your arm down here in the subcutaneous, okay? And above our arm we have the dermis layer and the epidermis. And then, of course, the sun is beaming down all energies, UV, A, B, and C, but hopefully within our stratosphere, UVC is all eliminated. So UVC is all eliminated because it actually is used up as it breaks O2 bonds. So now we'll be talking more about structures for compounds or structures for molecules. But the O2, remember we said that oxygen is diatomic? It actually has a double bond, has oxygen, double bond oxygen. The UVB then is partially gets through the stratosphere. It is slowed down with ozone in the stratosphere, but some of it gets through. And then the UVA, the atmosphere comes right through the stratosphere, and your textbook will say the reason that it gets farther into our skin is because even though it's less energetic, the UVB just kind of loses all its energy right at the top. So UVA and UVB can both do that. This slide, again, this is striking, and I'm not sure why this works. I bet your sister does. But as it comes down to getting a cancer of the skin, the folks who are most hit hardest are white males, and then followed by white females, and then down here we have black males and females. Now your textbook talked about with an increase or a decrease that I didn't see in the data, so I'm not quite sure. But these are the number of deaths per year, rate in people given 100,000 people. So it looks like the word I have here is radicals, free radicals. I was talking more to my husband Carl teaches in this class, and I was asking, so now how do those free radicals work? So he explained it to me, and I was like, oh, okay. But anytime you see something called a free radical, think that it's very reactive. And then we're going to be talking more about this. Think of, if you see the structure of some of this free radical, you're going to see it has an extra little electron, okay? So that free radicals are very reactive, and they have what we call an unpaired electron.
But it just wants to pair with things.
What's that?
Because it just wants to pair with things.
Yeah, it has an unpaired electron that wants to pair with things, exactly. That's what makes it reactive. So that was UVA. UVB then actually, I got this wrong. Wait, no, yeah, UVB actually is what gives us, it interacts and causes melanin to be released in our skin tissue, and that's what makes our skin look nice and brown. But that actually, if you've heard of melanoma, that's kind of where that word comes from. So what makes a nice tan skin is actually, and again, I can remember Amber talking about this, what makes your skin nice and brown is actually your body's reaction to a mutation that's been caused by energies from the sun messing with your DNA. So
tan people are mutants?
Mm-hmm. Mm-hmm.
Good. I'm not.
So yeah, tan people are mutants, and when they talk about getting a nice base tan, you know, it's like, oh, you get a nice base thing of mutated skin. So I don't know.
But it does, it keeps you from burning more, I guess.
Yeah.
The first time I get burned.
Yes, yeah, there is something to be said for that. So, but now vitamin D actually is created by your skin as your skin is exposed to sunlight. So there is kind of this sort of trade-off. So too much ultraviolet exposure can give you eye disease and cancer, but you need it to create vitamin D. Looks like I have the word sunlight up here. Most skin cancers are limited to exposure to sunlight. Skin cancer can appear at any age, but it's more common in older people. And the reason it is because item number 3 up there is that even though you may not currently be being exposed to the sun and all that, the past will come back to haunt you. UVA, the least energetic, is most strongly linked with cancers. However, UVB also is a player. So cancer can arrive in different cells. Cancers in, I think I had the word melanocyte, melanocytes, different cancers. So,
what's squamous? Says those in basal and squamous cells are common.
Sure. I'm not sure. Done with this part?
What's that?
How much we got?
2 more slides.
Yeah, but it's time back.
Was it?
Yep.
Was it time?
So we'll do those 2 slides on Monday. Hopefully we'll have more people here.
Yeah, what the? Why are they even?
Don't get me started. Well, attendance has been very good.